Part 2 by Mary.
Cool. Okay. We'll wait for folks to finish filing in. While we wait for folks to finish filing in, consider submitting a speed talk. Hey. Okay. So now we are all back for talk 2, which, so recall the outline was talk 1, this basic paradigm, which now we've seen. Okay, it's not quite fair to say we've seen it 3 times because the last one was kind of, but we've seen it at least 2.5 times. So hopefully we're on board with that. And talk 2 is sort of about what we can do on top of that basic paradigm. What are various techniques that we can use to make that better? So quick recap, because I know it's been a long 20 minutes or whatever. When we last left our heroes, algebraic codes, what was going on? So we saw 2 problems. We saw the unique decoding problem and the list decoding problem. So the unique decoding problem, our goal was to handle a number of errors, which was less than half the distance or with less than half the distance. And for Reed-Solomon codes, the distance, that should be times n. The distance is 1 minus r times n, about. And so we wanted t to be about this times n. Sorry for the typo. And if that's the case, then we know when we see this received word that there's a unique code word we can decode to, and we want to do that efficiently. We also looked at the list decoding problem, where we are allowed to take t a little bit bigger. Again, there's an n missing there. We want t to be 1 minus r times n. Sorry. And the goal is to recover all of the code words in that ball. And implicit in that statement is that if we want to do that efficiently, that there ought not be too many code words in that ball. That's what we're hoping for. We saw an algorithmic paradigm to do this, which had 3 steps. 1, interpolate some polynomial. 2, assert that that polynomial explains our target function f. And 3, use that explanation to solve for f, or solve for some small list of possibilities. Cool. Okay, so this is what we did last time. We saw this, saw several examples of this for both unique decoding and list decoding. And what we're going to do this time, for the next hour or so, is see how we can improve on this. There's still more to do. Can we make these algorithms faster? People were asking about the complexity, and I was like, polynomial time, do linear algebra, whatever. We'll see how we can make this faster, near linear time. That's going to be our goal for the second half of the talk. Can we get smaller list sizes? And can we work over smaller fields? Right? So last time we were always working over these big fields, but like often we really want to be working over F2. How can we do that? So today we're going to, or in this talk, we're going to answer those questions. So techniques to improve this paradigm. So here's going to be a list of techniques, and along the way we'll sort of see where they stop working and what the open questions are. So the first technique I'm going to talk about is locality, or sort of leveraging locality. So how can we speed up algorithms by running them on smaller bits? This is going to be real fast because we have a whole 2 hours of locality later or more by Elena. So this will just be a teaser. The second technique I'm going to talk about is distance amplification. So basically, one of the punchlines of technique 1 is we can make faster algorithms, but at the cost of getting worse parameters. And so then we'll see some techniques for getting the parameters back in line after we do that. The third technique I'll talk about is alphabet reduction. We'll see 2 different ways to do this. One, code concatenation, and the second, I'll just mention very briefly, using algebraic geometry codes. And if time, I have a 4th technique to talk about, which is how to exploit structure in the codes and the algorithms. But I'm not sure if we'll get to that. But if we do, then it's there. And if we don't, then that's fine. So we'll talk about all of these different techniques. And yeah, along the way, highlight sort of several open problems and what's still left to do here. And as usual, or as with last time, please do interrupt me and ask questions. So I anticipate I won't be able to get to technique 4, even if I don't get to some of these techniques. Like, that's fine. Like, I want to make sure people understand. Cool. Okay, so let's get started with locality. And as I mentioned before, we have a whole talk series on locality later in the workshop by Elena. Where's Elena? Yeah, by Elena. Yay. So this is just a teaser. But so the idea of locality, at least in the context of algorithms for algebraic codes, is we want to somehow either make a big code out of little codes or view a code that we already have as being made out of littler codes. So let me see. I'm just going to describe this with a couple of examples rather than a formal definition. This is sort of a hand-wavy thing. So one example of this is tensor codes. So suppose we start with the code C, subset of sigma to the n. We can define C tensor C. So this is going to be a code with longer block length. It'll have block length n squared instead of n over the same alphabet. And we're going to define it as follows. So it's going to be the set of all n by n matrices A, such that all of the rows of A lie in my base code and all of the columns of A lie in my base code. So if I look at any row or column, I get something that's in the base code. And more generally, you can define C tensor dot to dot tensor C in the natural way. So you take a m-dimensional tensor and every this one and that one and that one and whatever need to live in the code. This makes sense? Cool. And this is some way of making a big code where it has lots of little codes in it, because I have this code word in my big code, and then there's like all these little code words from the little code floating around. Another place where we see this is in multivariate codes. So for example, I'll just draw a picture of bivariate Reed-Muller codes. So a bivariate Reed-Muller code, this is like the bivariate analog of the Reed-Solomon code that we saw last time. So the code words are, again, I'm going to think of them as matrices, where the rows are indexed by field elements beta, the columns are indexed by field elements alpha, and what goes in the alpha beta place is f of alpha beta for some low degree polynomial f. So this is the Reed-Muller code, the bivariate Reed-Muller code of dimension, or of degree at most k, or degree k minus 1. And this has this same notion of locality in that we can find lots of little Reed-Solomon code words floating around here. So if I take any line in f squared, so I have this like this space f squared, and I look at any line here, and I look at the restriction of this code word to that line, what I'm going to get is a univariate polynomial, right? So basically just a Reed-Solomon code word. So any line that I take in this square, the picture isn't quite right because it doesn't look like a field structure, but imagine it wraps around or something. And any line that I take in this square looks like a Reed-Solomon code word. So I have all these like little code words from some other code embedded in my big code. Another example is lifted codes. So I could imagine instead of this definition here where I say, okay, I'm going to define it like this, and oh, hey, it just happens to have this property that when I restrict to a line, I get something in my original code. I could actually just define the code that way to begin with. Like I could define it to be evaluations of all of the bivariate polynomials f, all of the bivariate functions f, so that when I restrict to a line, I get something in the code. Right? This turns out to be different. This is called a lifted code. And you might think that if C is a Reed-Solomon code, that these are actually the same, that the Reed-Muller code words are all the things that restrict to lines. In some parameter regimes, that's true. It's actually not true in general, fun fact. And I think, Elena, are you going to talk about that? Lifted codes? Maybe a little bit. Okay, so stick around for Elena's talk to see more about that, or ask me later. This is a cool phenomenon that is not related to this talk, so I'm going to skip by it, but it's a fun fact. Anyway, so these are three different examples of ways that natural codes we can come up with that have little codes embedded in some bigger code. And the point for algorithms is that if we have a big code made out of little codes, well, this gives us some algorithmic leverage, because then we can like run our decoder on these like little code words and patch them together somehow. And the hope is that, well, because the code words are little, then this is going to run very quickly, right? Even if I have an algorithm for my base code that takes time like n squared or something, if the whole block length is n squared, then all of a sudden that's linear time, not quadratic time, like yay. So that's the hope. Of course, there are lots of subtleties with this hope, like, okay, how do we patch things together? Like, and which little code words do we choose to run on? There are tons of little code words. If we do it on all of them, like that's going to be too slow. And lots of things like that. And then the thing I actually want to talk about here is that the parameters are going to get worse. So these first two things, I'll just sweep under the rug and say, for all of these different examples, there are ways to deal with it. But I want to just sort of mention what happens to the parameters. So for example, for tensor codes. Actually, I feel like I've just been barreling on. Other questions? I haven't said anything like super precise, but this basic paradigm makes sense? Cool. Okay, so yeah, so we need to figure out how to patch things together. You need to figure out like which of these little code words you want to leverage. How you do that is sort of a case-by-case basis, but like inevitably the parameters are going to get a little bit worse. So for example, for tensor codes, let's say that your base code C, say it has like really high rate and reasonably small distance. So like let's say rate 1 minus epsilon and distance epsilon. So we saw last time this is optimal. This meets the singleton bound. Like hooray, we have this optimal base code C. Let's consider C tensor C. It turns out that to get the parameters for T tensor C, you basically just square the distance and square the rate. So squaring the rate, that's still a high rate code. Like 1 minus epsilon squared is, to first order, 1 minus 2 epsilon. It's still close to 1. But the distance is now, or the relative distance is now epsilon squared. We wanted it to kind of be like 2 epsilon. So that's not good. So that this is not optimal. So whenever we do this, we're sort of moving away from this like optimal parameter regime we want to be in. And so that's going to motivate the next technique that we're going to use. I'm not going to talk anymore about locality because that's, again, just a teaser for our latest talk. But the next thing I want to talk about is distance amplification. I will go into a little bit more detail about this. And the idea here is, OK, let's say we've done this local thing somehow, but now we have a code that has a fast algorithm, but bad parameters. How do we get the parameters back in line? And distance amplification is a technique to do that. So yes, the basic idea is we'd like to transform a code we have into one with better parameters, ideally in a way that respects, that like plays nice with algorithms that we might have for that code. And so today, what I'm going to talk about is a particular technique known as AEL distance amplification. So AEL here stands for Alon, Edmonds, and Luby after this paper from 1995. And it's this technique has been used frequently since then, sort of in the algorithms for algebraic codes literature. I'll mention just one paper, this paper by Kaparti, Mir, Zui, and Surah from 2015, just because I think this is the first paper where I really appreciated the power of this technique. But it's been used, it's sort of in this algorithmic context in a lot of other places. I should mention also there are lots of other versions of distance amplification. So for example, you might be familiar with this sort of classic ABNNR distance amplification. There's also a more recent version, actually also with rate amplification by Cohen and Nikovitz and many others. But today, just to focus on one thing, I'm going to look at AEL distance amplification. Okay, so here's how this works. So we're going to have two ingredients that we start with. The first is our base code. So we need a high rate code, C, and we'll think of C as having a fast decoding algorithm, but maybe it can't handle very much error. So imagine this is something we get after doing this locality thing. So we have a code C, it's very high rate, like maybe we've tensored it up, so it still has very high rate, but it has teeny tiny distance. We have super fast algorithms for it, but can only handle a little bit of error corresponding to that teeny tiny distance. And we want to make it handle more error. So that's ingredient number one. Ingredient number two is a balanced bipartite expander graph. So it'll look like this. So what is this? It's a bipartite graph, and it has the following sort of nice pseudo-randomness property, where if I look at any set S on the right, small enough set S on the right, like this one, and I look at the vertices on the left, and I ask how much do these vertices touch that set? Most vertices on the left should touch that set about as much as you would expect. So for example, here, if I highlight all of the edges coming out of this set, okay, this set has size m/3 in this example, so I should expect like a third of everyone's, like a third of this vertice's edges to touch the set. And indeed, that's the case for this vertex that has 3 edges coming out, and one of them touches the set. And that's true for most of these vertices, but it's not true for like this one. This one has 2 edges. So it's okay if there's a few that have too many edges, but most of them should have about what you expect. I'm not going to be any more precise about this. Like I said, the first talk was the one where I actually did a little bit of math. This talk, very hand-wavy high level. You can ask me for details later. Okay, so this is what I mean by balanced bipartite expander graph. So what is this distance amplification technique? So say we have these 2 ingredients. We have our base code C, and we have our expander graph. What are we going to do? So I'm going to start with the code word from C, and what I'm going to do is I'm going to show you how to transform that into a code word from some new code that I'll define by this transformation. Right. So the first thing I'm going to do to C is I'm going to chop it up. So I'm going to chop it up into chunks of some particular size. And then I'm going to take each one of those chunks and encode them with a little tiny Reed-Solomon code, or maybe a folded Reed-Solomon code, or a code of my choice that has the properties that I want. And basically the idea is I'm going to end up with a final code that sort of mimics the properties of this little code, but like in a big scale and with linear time algorithms. So I'll encode each chunk with a little Reed-Solomon code. And now it is expander time. Yay. There's less enthusiasm. Now it's expander time. Yay. All right, there we go. Good. Yeah, so now it's expander time. And so what we're going to do is we're going to take our bipartite expander, and we're going to use it to shuffle up the coordinates here, like shuffle up the symbols. So what is that going to look like? I'm going to instantiate a new code word over here. This is going to be our final code word. And I'm going to populate it with the symbols from this code word, but sort of munged up according to the expander. So what does that look like? So let's suppose that this first symbol here, I should say the vertices of the expander correspond to chunks in this vector here. So this first chunk, let's say it has 3 symbols in it. It corresponds to this vertex. And the number of symbols in this chunk should be the same as the degree of the vertex, which fortunately it is in my little example. And now what I'm going to do is I'm basically just going to ship these symbols across the expander. So this alpha, that's the first symbol, so I'll send it across the first edge over there. The beta is the second symbol, so I'll send it across the second edge. And gamma is the third symbol, so I'll send it like across the third edge like that. Does that make sense? And then I'm going to do this for all of the different symbols. I'm not going to do that many PowerPoint animations, but you can sort of see where that's going. So for example, down here, if I had like alpha prime, beta prime, gamma prime, those would end up sort of in the symbols that were connected to this vertex. Does this process make sense? It's very obnoxious to write down formally, but hopefully a picture is okay. Okay, and so then once we do this, this green thing here on the right, this is going to be our new code word. And here, just like with folded Reed-Solomon codes that we saw last time, we're going to take our alphabet to be larger than our original alphabet. So our alphabet symbols are now these kind of folded symbols. They're symbols, they're vector valued. So our alphabet is going to be F to the S, where S is whatever the length of these little chunks are. Does that make sense? Okay, so now I have a code, which I define by, for every code word in C, do this process, get this code word, and my new code is all of these new code words. Why have we done this? Let's see what happens when we want to, say, correct some errors. And hopefully I'll describe the decoding algorithm, and that will explain why we wanted to do this in the first place, and then we'll kind of wave my hands about analyzing it. Okay, so suppose that there are some errors. And remember, my symbols here are these big mega symbols. So that means errors are going to occur at the level of mega symbols like that. So say there's some errors like that. And let's see what the decoding algorithm does. So the first thing we're going to do, at least as a thought experiment, is kind of like, let's imagine propagating these errors backwards to where they came from. So we're going to propagate them sort of back across the expander graph. And so there were sort of 6 little symbols in error here, 2 mega symbols. And we have these 6 little symbols in error here, but now they're all spread out over all the mega symbols. And the property of this bipartite expander was that, right, for any set that looks like this, most of the vertices over here touch it in about the number you'd expect. And so what that means is that most of the chunks over here have about the expected number of errors. So what we've basically done here with the pseudo-randomness of this expander graph is sort of turned worst-case errors into something kind of like random errors. Each chunk has about what we'd expect, or most chunks have about what we'd expect. And that's great, because if we, let's say, design this little Reed-Solomon code here to handle the amount of errors that we expect, that means that most chunks we can actually correctly decode. So let's try to decode those little Reed-Solomon codes. And almost all of them will turn out well. Of course, there might be a few vertices like this one that touch the bad set too much, and they have too many errors, and that one's going to be wrong. But it's not too many of them. Okay, so now we're back here. We have that most of the symbols are correct, except for this one maybe. So our next step is we're going to just unchop things up. So again, we get most symbols that are correct, except for a few that are wrong. But now we can use the properties of C, right? Remember, C, capital C, was a code that had a really fast decoding algorithm, but it couldn't handle very many errors. But now, look, like we have way fewer errors now than we had to begin with, so we can run C's algorithm, and that works, and then we can correct the whole thing. So that's the basic idea. Does this make sense? Those questions? Okay, so let me wave my hands about parameters real quick. Like, what is the rate of this code and how many errors can it handle? Let's say if we want to do unique decoding. Okay, well, C had high rate. This step of chopping things up doesn't change the rate at all. It just repackages stuff. This step does change the rate. And basically, the rate of this, the amount that the rate blows up in this step is basically just by multiplying by the rate of whatever the inner read Solomon code was. This step doesn't change the rate at all, because again, it's just scrambling things up. So the rate of the whole thing is the rate of the original code times the rate of whatever this little read Solomon code is. And if the rate of the original code is close to 1, then the rate of this whole thing is close to the rate of whatever the original read Solomon code was. And how many errors can it correct? Well, the error correction was really based on what could the little inner read Solomon code do, with like the expected number of errors. So it can correct basically the fraction of errors that the original read Solomon code could. So that's great. We've inherited this optimal trade-off between rate and distance from the read Solomon code, but now we actually have a much longer code, right? How long does all this algorithm take? Like, what's the complexity of this algorithm? Okay, munging up symbols can be done in basically linear time. Decoding, right? Maybe this is slow, relative to these little block lengths, but these are really short. So overall, this is also really fast, basically linear time. And then unchopping and correcting, right? The whole point was that C had this really fast, maybe near linear time decoding algorithm. So altogether, this whole decoding process can be near linear time, but we've inherited those optimal combinatorial properties from the inner read Solomon code. Does that make sense? Cool.
If we use the folded read Solomon code, what changes?
Great. Yeah. So what changes if we use a folded read Solomon code? So for unique decoding, not too much, but this is a perfect segue into my next slide. What if we want to do list decoding? Or yeah.
The question about, in the last column, you say, okay, I'm going to attack this block of 3 letters as my larger letter. Mm-hmm. So I'm just curious, why is that my error model versus an adversarial error who just picks every small letter?
Great. Yeah. So the question is, why is this allowed? Why can I just say, I decide the alphabet size is Q to the S? Yeah. So it depends on the application and the error model that you have in mind. So you're absolutely right that in a lot of different settings, the natural error model acts on bits. And this is just not right for those settings. We will see next, I think, how to actually leverage this for those settings, but there's another step that needs to be done. However, there are settings where it makes sense to say, oh, the natural unit of errors is a large alphabet. So for example, in distributed storage or something, you might say, what's the failure mode? That whole server goes down, right? And in that sort of model, a larger alphabet size sort of naturally makes sense.
Yeah, that's perfect. Thanks.
In practice, do I just pick a fixed bipartite, balanced graph of every size, or is there some notion of matching the graph to the problem I have?
Great. Yeah. So the question is, how do I pick the graph? So I do need to match this graph to the problem that I have. In particular, what do I need? I need the number of vertices to be the same as the number of chunks, and I need the degree of the graph to be the size of the chunks. And yeah, typically, I'm not going to work through the parameters because it's a mess, but typically the number of chunks is order n and the size of the chunks is order 1. And there exist explicit constructions of expander graphs that for many such parameter regimes. I think it is a fair critique that you often have to take n fairly large to find good constructions of these. There's some caveat there. More questions? They're really good. Yeah.
In a practical application, could you to get around the alphabet size thing, could you randomize the choice of expander graph and send that beforehand, and then so that that you get around, so the adversary is not able to know where to concentrate its errors to screw you up or whatever? Does the question make sense?
Right. Yeah. So I think the question is like, well, I guess there's two things there. One, can I just pick a random graph? And the answer is that will have this combinatorial property with high probability. So even for a worst case adversary, that will be fine with high probability. But then also, can I do something random
Well, I guess
like
what I'm
after
saying-
the adversary goes?
Things like the alphabets, the large alphabet size is kind of putting a restriction on the adversary that it can only corrupt within, a block at a time. Could you get around that somehow by like randomizing the choice of the graph so that it doesn't know where to concentrate its errors to kind of screw you up on the other side of the graph?
I see. Yeah, maybe we can talk more about that particular suggestion offline, but in a moment I will talk about like, yeah, I have a whole chunk coming up on like how do we turn this stuff for big alphabets into stuff over small alphabets, and there will be some randomness involved there, and maybe that's sort of close to kind of what you're alluding to. So maybe hold that thought for just a little bit. Yeah.
Is this transformation going to maintain the linearity of the code? I feel very confused when I see these blocks being broken up and then.
Right. Yeah. So the question is, does this maintain the linearity of the code? Sort of. So if my original code, let's say, has these little teeny symbols that live over some field f, and this original code is f linear, then this final thing is still going to be f linear because, like, we shuffled things up, but like permutations are linear.
Right. Sure.
If your original code, if like, I guess it could make sense to think about this as your original code, and like maybe these blocks were linear over some extension field or something, then that will be destroyed. But yeah, linearity over the small field will be maintained. Was there another question? That was your question. Cool. Okay, so maybe in the interest of time, let me move forward. Hopefully everyone gets the basic mechanism here. But I want to go back to Henry's question, which was, right, here was Reed-Solomon codes. I have this little asterisk. We could use folded Reed-Solomon codes. What would that get us? Well, what we saw, or what we kind of very quickly waved our hands at the end of the previous talk is that folded Reed-Solomon codes can do list decoding better than Reed-Solomon codes. So this whole picture was for unique decoding. What if I want to do list decoding? What if there's too much error? Then these little Reed-Solomon codes wouldn't know what to do. But if I had a folded Reed-Solomon code, I would know what to do. And so this is a good opportunity for a quick aside on list recovery. Yeah, so the previous cartoon showed how to do unique decoding. What about list decoding? So let's go back to this cartoon. We're like halfway through. And let's say we want to do list decoding now. So the rate of the inner code, which should now be a folded Reed-Solomon code here, is too high to handle this amount of error. Right? So let's say it's a folded Reed-Solomon code. So maybe I can list decode instead of uniquely decoding. And what that's going to give me is a short list of possibilities for each one of these chunks. And most of them are going to be correct, meaning that the right answer is contained in those lists. And some of them might be wrong if there were too many errors that ended up in that thing. And now we have the problem of, from this situation, going back to the original code word C. Right? How do we do that? Right, so the problem here is we want to go from these input lists, this A, B, C, D, E, F, dot, Y, Z, back to C, or to a short list of possible Cs. So we want to generate a list of all possible Cs that agree with these lists. And this problem is known as list recovery. So here's an informal definition of list recovery. We say that C is list recoverable if given sort of short input lists, one for each symbol, you can efficiently find all of the code words in C, and implicitly this means that there are not too many of them, so that CI lives in SI for lots of I's. So that's exactly the problem that we just saw. And this problem has a name. It's called list recovery. Fun exercise. Folded Reed-Solomon codes actually are efficiently list recoverable as well as list decodable. I'm not going to work it out, but hint, we already saw the algorithm. So if you haven't seen this before, do it on your own. The same Gauss-Swamy-Lane algorithm will also work here. Okay. So what that means for distance amplification is, let's say if we take our little inner codes to be folded Reed-Solomon codes, and we take that outer code C to be some list recoverable code with fast algorithms, which we'll say how to get in a moment, then if you have a high rate code that can handle a little bit of error, then you can transform it into a rate R code that can handle the optimal amount of error for rate R for any R that you choose. And that's what this AEL distance amplification gets you. So it's a very neat technique. Cool. Are there questions about this before I move on to?
So in the definition of list recovery, this S1, S2, etc., they can be overlaps between them because the way you have showed as if there were no overlap.
Oh, yeah, that's right. Yeah, these S1s, S2, they can have overlaps between them. Yeah, I guess I showed A, B, C, D, whatever, just because I didn't want to do some scripts. Yeah, that's right. Yeah, more questions? Cool. Okay, so where are we? So far we've said, all right, technique one, locality. Let's come up with a code that has real fast algorithms, but real bad parameters. All right, distance amplification. Let's transform this code to get the parameters back in line. But as several of you just pointed out, like, hey, that makes the alphabet size real big. Why is that allowed? Sometimes that's allowed, but sometimes that's not ideal. So our next technique is going to be 2 different ways to reduce the alphabet size. And we're going to start with code concatenation, which is sort of the most natural thing to do. Yeah, so alphabet reduction, right? So far, all the codes we've been talking about have big alphabets. Reed-Solomon codes need big alphabets because they need the field size to be at least the number of valuation points. Folded Reed-Solomon codes have alphabet size even bigger because we did the folding. AEL, this distance amplification we just saw, might make the alphabet size yet bigger still. Again, this is fine for some applications, but like ideally we want binary codes for many applications. And I just want to take a quick aside to mention that this is a challenge. So lots and lots of big open problems whenever binary codes are involved. So here are some natural questions you might want to ask about binary codes. What is the best trade-off between rate and distance possible for binary codes? Open, right? This is one of the biggest open questions in coding theory. How about the best trade-off that we know to exist? So this is something called the Gilbert-Varshimov bound. It is attained by a random linear code. Looks something like this, right? So basically, as the distance, the relative distance goes from 0 to a half. So for binary codes, the best distance you can really hope for is like a half. Sorry, but by binary codes, I just mean that the alphabet is 0, 1. Yeah, so as we go from 0 to a half, the best rate we know how to get decreases something like 1 minus the binary entropy of delta. This is not that curve. This is a curve that I drew in PowerPoint. But the way to think about it, at least like down in this parameter regime, is that if you back off from this point by a half, if you back off from a half by a little bit, let's say by epsilon, then if you take a Taylor expansion of this, you can see that sort of the rate that you should get is something on the order of epsilon squared. So like close to this point, this is sort of like roughly looks like a parabola. Okay, so right, at least this one I have an answer for. What's the best trade-off we know exists? It's this Gilbert-Varshimov bound. Can we do better? Open question. However, we can ask, okay, so we know that these codes exist. Can we construct them? Right? This is also largely a big open question. So there's been like really exciting progress on this in the past 5-10 years. So for example, Tosh-Ma's code, which were a big breakthrough in 2015, 2016, something like that, and related constructions, these can get rate very close to the Gilbert-Varshimov bound, sort of in this parameter regime where we're real close to a half. So we now do have explicit constructions of codes there, but in other parameter regimes, big open question. And you might ask, okay, how about algorithms for those explicit codes? So we do have algorithms for Tosh-Ma's codes, near linear time algorithms, which are very exciting. So for example, these works by Geronimo Srivastava-Tulsiani and also Blanc and Duran for related code construction. These are near linear algorithms for these codes, but again, for these explicit codes, but again, that's sort of only in this very low rate parameter regime. So there's tons of open questions here, like what is the right answer and how do we get it? These like very, very general questions. So there's huge challenges there with binary codes. Okay, so with that backdrop, let me tell you how we can get close to binary codes. Cool. Okay, so the plan for alphabet reduction techniques is first I'll talk about code concatenation, and then I'll talk very, very, very quickly about algebraic geometry codes. And then we'll see an aside, which is, this is probably where the talk's going to end. Like, what does all this get us? I'm throwing these techniques at you. What happens when you actually use them all together? What can you get and what can't you get? And that's what I'll do. Okay, but first let's see this technique, code concatenation. So this is like the first thing you would try to do when you have a code over a big alphabet and you want it to be over a small alphabet, basically you take your code word, so it has all of these symbols that live in a big alphabet, and basically what I'm going to do is I'm going to treat each symbol as a little message, and I'm going to encode it with a little binary code. So let's say that C prime is some little binary code. I'm going to take C1, the first symbol here of my code word, and encode that with my code C prime to get a little binary vector. I'll do that for all of them, and then I'm going to get a final code word that is binary. It lives in 0, 1 to the something. Make sense? Cool. Okay, so algorithmically, this seems great, right? In terms of like decoding algorithms, right? Even if even if I don't have any explicit constructions or even any good algorithms in the parameter regime that I want for these binary codes C prime, if they're small enough, then like brute force counts as efficient, right? So, okay, I see some people being like, theorists. Yes, I know. Yeah. Yes. Oh, good. Even to a theorist. Open problem. Make that better. Yeah. Okay. Good. Yeah. But combinatorially, it's not so great even for a theorist, right? Because the final, so when you concatenate, what happens is basically you multiply the two rates and you multiply the two distances. So even if, what that means is that even if your original codes, both the outer code and the inner code that you start with are optimal, their composition is not going to be, or the concatenation is not going to be. So we won't be able to handle the right amount of worst case errors if we wanted to do this. So side note, actually, this can optimally, for some flavors of theorists, handle random errors, C40s, concatenated codes. That's a different talk. But for worst case errors, this is not great. So instead, what I want to talk about is a technique due to Temesson. And the basic idea here, and this is maybe close to the question you were asking about, is what I'm going to do is I'm going to choose different inner codes for each position. I'm going to choose them randomly. So just random linear codes, IID. So I'll start out with my outer code word here, and I'm going to concatenate it. The first symbol is going to be encoded by a random linear code C1 prime. The second symbol is going to be encoded with a random linear code C2 prime, and so on. So this is a randomized construction, but Temesson in the 80s showed that this actually approaches the Gilbert-Barshamov bound. So this attains, well, we don't know if it's optimal, but like the best trade-off we know how to attain for binary codes between rate and distance. That's pretty cool. And moreover, the thing I want to talk about now is actually if the outer code is list recoverable, which we just defined, and also is in the right parameter regime, then not only does this have optimal trade-offs, but there are efficient algorithms to decode it to half the distance. Right? So we said that we didn't, like, even though it's a really hard problem to come up with explicit constructions of these codes with or without efficient algorithms, actually there are randomized constructions of these codes that do have efficient algorithms. Yeah.
What is the outer code for Thompson's construction for the approaches G?
Any MDS code.
Yeah, okay.
But yes, resolving code, for example. Yeah, all it needs is, yeah, anyway. Yeah, other questions? Yeah.
Could you give me intuition for why, in this case with the randomized construction, we don't end up losing on the rate, like why the optimality don't multiply out and get sad?
Right. So the rates do multiply. That's still true. With distance, I guess like the reason you multiply the distance in the other thing, like in the analysis of the other thing, is that it's sort of a very worst case type of notion. Like the thing that can go wrong is that if the adversary chooses to clobber like each of the symbols just enough to like make them, like chooses to concentrate their errors like just right, then it can throw things off. I'm sorry, I'm not being very precise, but yeah. Yeah, okay, yeah, and then somehow this gets around it. This gets around that risk perception.
And so it is the idea that the adversary doesn't know your randomization, like doesn't know your random coins?
No, so the adversary does know the random coins. This is still a worst case statement. Yeah, but we can take this discussion offline. I don't have, I have very technical intuition, which won't make sense when it comes out of my face without a whiteboard marker. Yeah. Does anyone have like good short intuition? Yeah, okay, like the analysis works and then it doesn't. Yeah, I don't know. Yeah, both of these are not too hard to show, so I can maybe walk you through it later. Yeah, cool. Okay, yeah, but what I'd like to do now is give some intuition about why this is the case, because this should motivate, like lots of people were asking when I was like, look, we get these really high rate codes with fast algorithms over enormous alphabets that are list recoverable. Like, why do we care? This is one reason why we might care. So let me say sort of how you do this. So suppose that, let's take for granted this result that these things approach the Gilbert-Marshall bound, and let's say that t, the errors, are as close to n times delta over 2. So we have close to half the distance, and we want to correct it. All right, so what does that look like? So here's our sort of concatenated code, and in our picture, we're going to have our sort of geometry picture over here that we keep having as we walk. And then a bunch of errors get introduced, and they get introduced however the adversary wants to introduce them. So maybe this whole symbol gets awkward or something like that. And here, what that looks like is this. So we know that the code combinatorially is uniquely decodable for this fraction of errors. So we know that there is a unique code word that is t close to it. Right? We just want to find it. So what are we going to do? Here's the algorithm. Did I not have a citation on this slide? I think this is first due to Gorsami and Indik idea, and then has been built on since. The basic idea is let's list decode each inner code by brute force. Again, because they are so short, and I'm a theorist, I'm going to call this efficient. And now what I'm going to get is a set of possible symbols for each one of these outer code symbols here, right? Again, to Lolita's point, I'm just being kind of sloppy by drawing these as distinct. They could be arbitrary, but whatever. Cool. And then this is now we can use our list recovery algorithm for the outer code. I have a short list of possibilities for each symbol, and I have this supposedly now this outer code that is list recoverable. So let's do that. And now I get a short list of possible code words. So in this picture, maybe that short list looks like this. But combinatorially, we know that only one of them is close. And if I have a short list, even a polynomial sized list, that still gives me an efficient algorithm, right? I take this short list, I check everything in it, I pick the one correct answer, right? So by Tumessen's result, at most one of these things in this list is close to the received word, just try them all and find it. And that gives us an efficient algorithm to uniquely decode this concatenated code, as long as I have an efficient algorithm to list decode or list recover the outer code. Does that make sense? Cool. Okay, so punchline from code concatenation here is that even though it's open, it's a big open problem to construct explicit codes of rate, maybe like bounded away from 0 that approach the GB bound. We can get randomized constructions of these codes and decode them efficiently. And if you're interested in parameters, hold on for just a few slides and I'll get back to that in a second. Cool. Okay, so how long do I have? Like 10, 15 minutes? Yeah. Okay, cool. So let me very quickly say one other technique for alphabet reduction, and that's using algebraic geometry codes. So as a motivating question, we might ask, okay, why do Reed-Solomon codes have such big alphabets? Well, it's because we needed lots of different evaluation points, right? If I have just one evaluation point and I evaluate my polynomial at all of those points, this does not give me a very interesting code, right? This is just the repetition code. So we need distinct evaluation points. And so we asked ourselves, well, is there some way we can get more evaluation points without making the field size larger? And this is sort of a very basic idea of AG codes. Huge disclaimer, I am so far from an expert in algebraic geometry codes. There are people who have much more expertise in this room. But here's my real quick picture. So take some nice algebraic curve, call it curly x. This is my picture of a nice algebraic curve as rendered in PowerPoint. Let's look at all of the points on curly x that lie in FQ, or that lie in FQ at the end. And the hope is so many points, way more than Q points, if our curve is like, nice and curvy, got lots of points on it. And then we're going to take our set of functions curly f to be some analog of low degree polynomials on that curve. So I think formally you pick a bunch of functions in some Riemann rock space. And then we're going to define our evaluation code as usual. So take all of our functions that live in curly f, evaluate it all on these points in P. And now, hooray, we can take the field size to be smaller because we got all of these points for free because we used this cool curve. So punchlines are that you can get Reed-Solomon-like codes over constant size alphabets that are still amenable to this basic paradigm that we saw in the first talk. Interpolate some polynomial kinds of roots. In fact, you can even get codes over constant size alphabets that actually beat the GB bound. You just can't get binary codes. But there are codes over, let's say, F49 that beat the GB bound. Cool. Okay, that's all I'm going to say about algebraic geometry codes. Ask a mathematician. They'll tell you more. Great. But what I wanted to do to wrap up the talk is talk about what do all of these techniques get us. So I've given you a bunch of different I've told you about a bunch of different techniques that we can try to use on top of this framework of interpolate a polynomial and find some roots. What happens when we do it? Okay, so here's just one example. So these techniques have been used in lots and lots of papers altogether, but I'm just going to pick one example. This is a paper by Brett Hemingway, Noga Ranzui, and myself from like 5 years ago or something. And this uses literally all of the techniques we've seen so far on top of each other, which is why I picked this one. Okay, and so here's basically what this paper does. You start with an algebraic geometry code that is list recoverable. So here's technique 3B that we just talked about, algebraic geometry codes. So we use one that's due to Guruswamy and Jing. And then we use this basic interpolate a polynomial and find the roots paradigm to come up with the list recovery algorithm. Okay, we have this, but it's slow. The algorithm is slow. So what do? We use technique 1, locality. Take a big tensor product, tensor it up. And what we end up with is a high rate code with fast list recovery, but really terrible distance. So it can't handle very many errors at all. Okay, what do we do next? We do this AEL distance amplification. And that's going to give us an optimally list decodable code with fast algorithms over a real big alphabet using that technique that we saw. And then we can concatenate and do this Temesson technique that we just saw. And that's going to give us a randomized construction of codes approaching the GB pound with fast algorithms. You can do that all together. And quantitatively, the punchlines that you get are, so if we're interested in list decodable or list recoverable codes, that's this box here. We can get list decodable codes with any rate R that you want, radius sort of approaching optimal, so n times 1 minus r. If you remember from the first talk, this is what we wanted. Alphabet size, very close to linear in n. Decoding time, very close to linear in n. And list size, sublinear in n. So those are the punchlines. And if you care about binary codes, what you can get is any rate. Okay, it can't be too big, but at least it can be as big as a constant. So anything less than 0.02. And distance delta with approaching the Gilbert-Barshamov bound. So the rate is approximately 1 minus the binary entropy of delta. And it has unique decoding algorithms up to half the distance, running in time near linear, n to the 1 plus 2. So these are all the punchlines. If I describe it like this, it's like, well, everything is solved, isn't it? But these are very rose-tinted glasses punchlines. So what I want to do in the next slide is maybe take some of the rose tinting off and talk about some open questions that are left here, aka the dirty truth. And yeah, so the dirty truth is that basically each time we apply one of these techniques, like they're very cool and very powerful, but every time we apply one of them, the dependence on some other parameter that we don't like to talk about typically gets worse. So for example, for all of those like glowing punchlines that I said on the previous slide, don't ask me what the constants are, don't ask me how big n needs to be, and please don't ask me what the dependence on the gap to capacity is. Right? So if the rate is going to be epsilon off from the Gilbert-Barshamov bound, what's the dependence on epsilon? Okay, so you can ask me, I will tell you, it's in the paper, we worked it out, but it's embarrassing, right? And so I think, and I think that the reason that I don't want to answer these questions in public is, I mean, the reason is because I am a classy person, but the technical reason is because, yeah, basically every time we apply one of these techniques, something gets shot up some exponential power, basically. And yeah, so the big open question here, a big open direction that I really want to highlight is that these techniques are great and they've gotten us really far, but I think we need something new. So either a new way to combine these techniques or different techniques in order to make these algorithms actually practical, right? Like those punchlines that I said on the previous slide sound like they should be super practical, but no one is going to use this result in practice for very good reasons. And yeah, I think that new techniques are needed. Yeah, so this is something I really want to highlight. Great. Okay, so I have like 5 minutes. Sure. Cool. Okay, so maybe I do even have time for my technique 4. Yeah, so okay, so those are techniques 1, 2, and 3. Can be very useful, but I think there's a lot of work to be done to make these applicable in actually practical settings. I want to talk a little bit about technique 4, which I think is maybe more in the direction of that. And this is sort of exploiting structure that's maybe already present in the codes or the algorithms that we have, so that we don't have to apply these techniques on top necessarily. I have like 5 minutes, so what's the best way to do this? Yeah, so maybe I'll just give the intuition. So like, let's recall from talk 1. So this is the bit that I rushed at the end because I really wanted to highlight it. So it's good that I'm getting to this bit because I did that. That the Gersami-Wang decoder that we talked about, like the only thing I told you about it is that it outputs a subspace, right? It outputs a constant dimensional subspace that's guaranteed to contain the list. And it turns out other decoders as well also output similarly structured lists. So things that live in this interpolated polynomial and find the root paradigm, a lot of times they output some nicely structured lists. And so let's let curly L be the list that we want to return. So it's all of the code words that are close to our received word here. So if we know that our algorithm outputs a subspace, well, that tells us that curly L is contained in some low-dimensional subspace. So maybe the picture looks more like this. Like, here are all my code words. Here's this low-dimensional subspace that's guaranteed to contain the list. But what if my code avoids such structure, right? Then I know that actually the list is smaller than I thought it was, right? It's not going to be this whole subspace. It's just where the subspace intersects the code, right? So that means that the list is smaller than we thought it was. And this leads us to a few different avenues to try to exploit this. So the first is that we can try to modify the code, like maybe intersect it with some subspace-based extent, something that avoids subspaces, or take advantage of some other more precise structure that the decoder gives us. And there are lots of works that have done that to very good effect. And then there's another version, which is actually we can assert that the codes that we were interested in themselves already had that structure. We don't even need to do anything to them. And I find this very promising because, like I said, every time we do one of these cool techniques, something else gets swept under the rug. And so with this type of approach, we don't need to do that per se. So here's an example of how that would work. Like, suppose that C is a linear code with good distance. And suppose that curly L is this list that we want to return. And suppose that we know that the list is contained in some, let's say, constant dimensional subspace. Then I claim that automatically, just from the distance of C, curly L is going to be smaller. It's going to be much smaller than that low-dimensional subspace. Even if curly C is a linear code, like it definitely doesn't avoid subspaces. It is a subspace, but it will still the list will still be much smaller than all of the subspace. So why is this true? So here's the basic idea, and this is from joint work with Compartey-Ranzoni and Saraf from a few years back. So suppose that here is this received code word G. Right, I want to find all of the code words that are close to, or sorry, not code word, received word G. I want to find all the code words that are close to G. So what I'm going to do first is let's choose a constant number of random coordinates and just assume that they're correct. So I'll pick a bunch of random coordinates and be like, those are right. I say so, right? And I claim that when I do that, that for any C, for any code word C in the list, there is a decent probability, it might be small, but like bounded away from 0, that C is the only thing in my subspace W that agrees with this advice. So why is that the case? So that this has two components. First, that C does agree with this advice. Why is that true? So C is likely to agree with the advice just because it's in the list. That means it's close to G. So it doesn't differ on too many places. So if I pick a constant number of places, there's some decent probability I won't hit any of the differences. Right? So C is likely to agree in these positions with G. And then I also need to show that nothing else in the subspace is likely to agree. And intuitively, the reason this is true is, okay, so I have some very low dimensional subspace, like some constant dimensional subspace, and it's a constant dimensional subspace of a code with good distance. So that means that all of the code words in that subspace are like really far from each other. And you can use that to show that, right, basically every time you grab a random position here and fix it, you're basically cutting down the dimension of your solution space by 1. You can show with high probability this is going to knock down the dimension of your solution space because of the distance. And so what that means is that, okay, you have a constant dimensional space to start with. If you knock it down a constant number of times, you won't have any degrees of freedom left. So C will be the unique thing in that list. Okay, great. So if you believe that, then, all right, what's the size of the list? Well, for anything in the list, if I have this same algorithm that returns it with probability P, so if you just sort of like do linearity of expectation, stare at it for a bit, you'll see that that implies that the size of the list is no more than 1 over P, which is actually, turns out, with these parameters, it's going to be much, much smaller than the size of W itself. So you can use this for any code with good distance, and if the code has a little bit more structure, you can actually do something even better. So what you get out is that folded Reed-Solomon codes themselves, also univariate multiplicity codes, which I haven't talked about, but which Prahlad will talk about in his talk tomorrow, I think. Folded Reed-Solomon codes themselves, with none of these fancy techniques themselves, are already list decodable with rate R, radius optimal, and list size smaller than it was before. Although the algorithms are still no faster. Follow-up work by Kaparti, Resh, Ranzui, Saraf, and Silas de-randomized this decoder. The decoder I described as randomized algorithm, take a bunch of random advice. They showed how to de-randomize this. And actually a very recent work by Tomo, this is like barely a month old, has a simplified proof and better bounds. This is really pretty. I'm still processing this paper, but you should look at this. But I think it is still open what is the correct list size for folded Reed-Solomon codes. So if you're looking for open problems. Cool. Okay, so I should probably stop. Yeah, all right, so let me wrap up real quick. Cool, so what have we seen? We've seen a bunch of techniques to improve this basic paradigm of interpolate a polynomial and find some roots. So technique 1 is locality, technique 2 is distance amplification, technique 3 is reduce the alphabet size. And we saw that you can apply all of these things all together to get very good results on paper, but there's a lot of open questions when it comes to making these actually practical. And then technique 4 is we can also additionally exploit some structure in the codes or the algorithm. And yeah, and I guess I did this after because I didn't actually expect to be able to get to it. But you can lump this in. You can do all 4 of them together. You can still get lots of, all of the things. Right. And of course, yeah, as I mentioned, there's still lots left to do. So those are the techniques that we saw. How about the open questions? So I mentioned a lot of open questions for binary codes. Right, so practical near linear time decoders for even probabilistic constructions of binary codes near the GV bound, and then of course explicit constructions of binary codes near the GV bound, so it is an open question in more parameter regimes than we currently have them. And over large alphabets, again, practical near linear time list decoding or list recovery algorithms and better list sizes. And I think if we could get these, hopefully I've convinced you that if we get really practical things, even if the alphabet size is huge, then with this sort of concatenation trick, we can perhaps turn that into better unique decoding algorithms for binary codes. Cool. But both might require new techniques. So I don't know, maybe instead of my little cartoon hammer, we need maybe a fancier hammer, or my hope is that we just need a simpler tool that we haven't thought of, like an IKEA Allen wrench. I'm hoping is something we can go for. But who knows? So hopefully we'll figure it out in the coming semester. Okay, so I'll stop there. It's time for lunch.
Thanks, Mary, for a very illuminating tutorial. And maybe time for a quick question if people have any. There were many questions during the talk.
Yeah, I just want to confirm the reason with tensoring is that the outer code doesn't have, like an AG code doesn't have almost linear time algorithm, so tensor to reduce to.
That's right. Yeah. So the question is like, why do we need to tensor things up? And yeah, it's because the original AG code, if we want a near linear time algorithm, it doesn't have near linear time algorithms. But after you tensor it up, then it becomes.
Okay. Any other quick question?
Is there ever a reason to tensor like different codes together?
Yes.
What would be one?
Yeah. So the question is there ever a reason to tensor different codes together? Yeah. So like for some. Actually, I think in that very paper, I think I was oversimplifying. I think we do want different codes. But like one, for algorithms, sometimes you want like one of the codes to have some nice algorithmic property and the other one to have a different nice algorithmic property, because then sometimes the decoding algorithm kind of like goes back and forth and leverages things. So yeah, there are reasons that you'd want to tensor two different things. I just didn't talk about it.
All right, maybe we'll take remaining questions offline. Thanks again, Mary.
Oh, and speed talks.
How long are the speed talks?
Ah.